All right, this is my artificial blood vessel project presentation done by me. So here's the base model in SOLIDWORKS. Data from scholarly sources was gathered, including the wall thickness, outer diameter, and flow rate for human blood in a male to be able to create this drawing. And this is the base drawing, figure 1. We have an outer diameter of 6 millimeters and a wall thickness of zero point 0.4 millimeters. And since this is 6 millimeters, it classifies as a small vessel diameter. So here is the base model creation in SOLIDWORKS. So the drawing was extruded, and the example given below in figure 2 is for the 100 millimeter ePTFE model. And 3 models were created for each material of each length of 1 millimeter, 10, and 100. And I will go ahead and show all 9 created models in the next slide. So on the left, we have the 100 millimeter models, the middle are the 10 millimeter, and the right are the 1 millimeter. In the red is the ePTFE, the gray is the PET, and the bottom is the polyurethane PE. Now here are the material properties for the ePTFE. The important ones are included, such as the elastic modulus, the Poisson's ratio, the yield strength, and the tensile strength, and the density. So those are all necessary to run the static simulations in SOLIDWORKS to gather the stress and strain values. And here's the same chart for the PET. Again, the important values listed in the chart. And finally, for the polyurethane PE, material properties are listed. So for the flow simulation, the base model of the 1 millimeter expanded polytetrafluoroethylene model was used to find the blood pressure to operate in the static simulations. This was done by applying the in and outlet velocities found during research of 11.5 centimeters per second, and then as well as the environmental pressure of 101.3 kPa acting the vessel. It was found that the blood pressure through the model was 16 kPa, which matches the healthy blood pressure of 120 millimeters of mercury. And this means that we found the final condition to be able to run that static simulation to get stress and strain values that we need. And I'll go ahead and go over the design and results right here. So here is the flow sim setup. So we have the inlet and outlet velocities denoting in the red arrows in the vessel, and the green or slightly blue in this case arrows denoting the pressure. And you can see on the left, the contour plot is dark blue, and that results in that 0.016 pressure. There also are lids in this model that are enclosing this vessel as an internal flow sim, but I went ahead and hid those for the sake of demonstration. And again, here is the pressure that we found of 0.16 MPa, which is the correct operating blood pressure for a human. So for the static simulations, a fixture was created on both sides of the vessel to prevent translation and movement during the running of the simulation. The internal pressure of 16 kP that we found in the last slide was applied to all 9 models as the operating condition normally. And then for the 3 100 millimeter models of each material, I decided to apply the extreme case scenario of 5 times the blood pressure of 80 kPa. And the inner and outer stresses and strains were calculated for every material, so there ends up being about 18 simulations results. And I will go ahead and go over the simulation models here. So on the left we have the expanded polytetrafluoroethylene models, and then in the middle we have the polyurethane models, and the right we have the PET models. So the stress and strain, inner and outer, are both probed right here. I went ahead and just went and showed the stress. So these are all stress simulations just for the sake of space, as there are 18 total simulations. So these models were probed, and the values were input into Excel data, and the yield strengths are also shown for reference. Here's data table 1. Important information calculated here is the factor of safety. That's done just by taking this yield strength here and dividing this yield strength by the max operating stress, which in this case of the 1 millimeter ePTFE is 0.02154 megapascals, which results in the factor of safety of 1067, which means we're operating 1,067 times away from the yield strength. And here's data table 2 for the extreme 80,000 kPa scenario. Again, factor of safeties are calculated just to give us an idea of how far we are from vessel failure. So for the polyurethane had the lowest factor of safety for all three materials at 92, 18, and 17 for the 3 lengths, respectively. And the extreme case scenario was 3.3 factor of safety, which is pretty concerning, as that's only 3 times smaller than the yield strength or the yield stress, which means that the part is close to failure. And obviously, we don't want that in someone's body, as it could fail and cause great injury. So I went ahead and I eliminated the polyurethane blood vessel as a choice in the final decision, just for those factors. The expanded polytetrafluoroethylene performed very well in the analysis. The factor of safeties were high at 1067, 202, and 195 for the 1 through 100 millimeter models, and the extreme case of 80,000 or 80 kPa was calculated to be 39, which is far enough away from the yield stress to be safe, which means it won't rupture under the extreme case scenario of 30 or 80 kPa. And finally, the polyethylene terephthalate performed the best. The factor of safeties were 1895, 349, and 336, which were twice or almost twice of the EPTFE. In the extreme case scenario, the safety was 68, which is the highest of the 3, and it's not at risk to burst just because it's operating so far from the yield stress. So it's going to be, so it's one of the materials in the running for the final decision. So the cost of the polyethylene terephthalate is relatively low. It's called Galgan in the medical field, but it's hard to come by due to the fact that the vascular graft, expanded polytetrafluoroethylene, is the leading vascular graft material. But Galgan tubing was found to be $18 roughly per 100 inches of material, and that's for a 6 millimeter by 0.5 thickness tube. It's already drawn and ready to use, so no manufacturing is required, and this was gathered from a polymer supplier, which is referenced. The expanded polytetrafluoroethylene, known as Gore-Tex in the medical field, is very hefty from the supplier directly, which is $400 for a 4-pack of 7 millimeters by 450 EPTFE grafts. There is cheaper options such as raw polytetrafluoroethylene tubing, which can be manufactured. The only issue is that it is not a tube, so it needs to be machined through either blown film extrusion or plastic molding. It's cheap at $13 for 1800 millimeters, which is less than the PET. So when compared to the expanded polytetrafluoroethylene, the PET has a higher factor of safety, and it's operating farther from the yield stress, but it's not necessarily a concern just because they're both far away from the yield stresses and they are both safe to use. So the cost is really the deciding factor, and the fact that the EPTFE is lower cost than the PET material is a good thing. And also the expanded polytetrafluoroethylene is the most used material in vascular grafts today. So I think that the expanded polytetrafluoroethylene is the best choice to be chosen to be incorporated into the blood vessel due to being safe, having a high factor of safety. It's cheap, the low cost, and it's well known by thousands of professionals that use it every day. So the expanded polytetrafluoroethylene is the chosen material. And yeah, that's it. Thank you for watching. Thanks for a great semester.